Friday or next.
Right? Why would I want to test it on Friday? Right? I'm not even finished with the material yet. Let's have it on Friday.
We'll start in a couple of minutes. All right, it's 9 o'clock. Today we'll look at section 9.3 on separable equations, differential equations that are called separable. We'll look at some introductory material from section 9.1 first. So a differential equation is an equation that contains an unknown function and some of its derivatives. The order of a differential equation is the order of the highest derivative that occurs in the equation. So an example of a first order differential equation, if we have y prime equals 3y, so we're assuming y is a function of x, and y prime is, in that setting, is dy dx, the derivative of y with respect to x. But the y prime notation is convenient in this setting, so that's just how to interpret it. A famous second order differential equation, this is just to show you an example of a second order differential equation, is this equation. This equation has the unknown function y. It has its first derivative, but it also has its second derivative. And since the highest order of the derivative is 2, this is referred to as a second order differential equation. A solution to a differential equation is a function that satisfies the conditions of the equation. So if you've never read or been taught anything about differential equations, you probably know more about them than you realize. So let's look at this example. Find a solution, and then afterwards find the general solution to the differential equation y prime equals 3y. So y prime is just shorthand notation for dy dx, and y is a function of x. So can you think of a function f of x such that the derivative of y with respect to x is 3 times f of x? Hey, how about this? I'll just make a suggestion. What if you have y equals e to the 3x? Then what's the derivative of y with respect to x? Three times e to the x. Yeah, three times e to the 3x. But e to the 3x is what y is, so this is just 3 times y. So we found a solution to that differential equation. One solution is just y equals e to the 3x. That is a solution because it satisfies the conditions of that equation. What do you suppose the general solution is? Well, if I multiply e to the 3x by any real number that's non-zero, I could just say, well, I want to assign y to be c times e to the 3x. And then we'll check to see if this is also a solution. So if you take the derivative of y with respect to x, you get 3 times c e to the 3x. And c times e to the 3x is just what y is. So dy dx is 3 times y. So this is just called the general solution to this particular differential equation. Not too bad, pretty easy to follow. Okay, in an application, solving a differential equation with an initial condition may be required. And this is referred to as an initial value problem. So let's solve this initial value problem. This time we have y prime equals negative 5y, and y of 0 is equal to 10. Y of 0 equals 10 is the initial condition. So we'll just assume that y is a function of x. And when x is 0, the y value is 10. Okay, so step 1 would be to find the general solution. General solution. So this is similar to the one we just did, just with a different constant. So if y prime equals negative 5y, then what should y be in this case? So some number times e to the negative 5x, right? So some number c times e to the negative 5x. And you can verify that dy dx is negative 5 times c times e to the negative 5x, or negative 5y. Hey, then to find the particular solution, we use this initial condition. So when x is 0, the value of y is 10. So we just replace, in this equation, in the general solution, Replace y with 10. Replace x with 0. So we get e to the negative 5 times 0 is just e to the 0. But e to the 0 is 1, and so the value of c is just 10. So the solution to the initial value problem is y equals 10 times e to the negative 5x. So it's pretty straightforward, this part of the differential equations. Okay, in section 9.3, we'll take a look at what are called separable equations. So a separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. So what that means is dy dx can be expressed as g of x times f of y. If f of y does not equal 0, then h of y equals 1 over f of y, and that implies that dy dx is equal to g of x over h of y. And then to solve this differential equation, we write the differential form. It comes down to fraction arithmetic. We write it as h of y dy equals g of x dx. And then we integrate both sides. So on the left-hand side, we have an integral of a function of y dy. On the right-hand side, an integral of g of x dx. And after integrating both sides, which includes a constant of integration, we'll then attempt to solve the resulting equation for y. So that's the general procedure for solving separable differential equations. So we'll do a few examples. So here's our first one. Solve the equation y prime equals 6 times the quantity 1 plus y squared times x squared. Okay, so I'll replace y prime with dy dx. And I'm going to rearrange this so that it's the quantity 1 plus y squared times 6x squared. Okay, so we have what this satisfies the definition of a separable equation. Dy dx is the product of a function of x and a function of y. So it's separable. So on the left-hand side, I'm going to have dy over the quantity 1 plus y squared. And on the right-hand side, I'm going to have 6x squared dx. So to get to this form, just think about, well, you can multiply both sides by dx first, and then afterwards divide both sides by the quantity 1 plus y squared, and we get this equation involving the differentials. Okay, then we're going to put this inside the integral. So the integral, I'll write it as 1 over 1 plus y squared dy. And on the right-hand side, the integral of 6x squared dx. And now we integrate both sides. We've integrated functions like this before. So an antiderivative of 1 over 1 plus y squared with respect to y, it's the inverse tangent of y. Inverse tangent of y is an antiderivative of 1 over 1 plus y squared with respect to y. And then on the right-hand side, we integrate with respect to x. So an antiderivative of 6x squared is 2x to the third. And we add a constant of integration. The goal, remember, is to solve for y. So if the inverse tangent of y equals 2x to the third plus c, well, we can write directly what that is, but if we use the inverse notation, if we compute the tangent of both sides, the tangent of the inverse tangent of y on the left-hand side, and the tangent of 2x to the third plus c on the right-hand side, okay, then the tangent of the inverse tangent of y is just y, and then the right-hand side is in the form that we want it, tangent of 2x to the third plus c. Hey, this is not an initial value problem, so this is the answer, where c is the integration constant. Okay, let's try the next example. Solve the initial value problem, y prime equals x squared times y, with the initial condition y of 0 equals 2. Okay, so y prime is what dy dx is. It's equal to x squared times y. So this satisfies the definition of a separable equation. Dy dx is the product of a function of x and a function of y. So we can separate them. I'll put in one more step than is really necessary. If you start by multiplying both sides by dx, we get dy equals x squared y dx. We want all of the y terms on the left-hand side, so we'll divide both sides by y, and we get dy over y equals x squared dx. Okay, then we put each side into an integral. So the integral of 1 over y dy on the left. On the right, we have the integral of x squared dx. Okay, an antiderivative of 1 over y is the natural log of the absolute value of y. And on the right-hand side, an antiderivative of x squared is x to the third over 3, and then plus a constant. Okay, we want to solve for y, so the the absolute value of y is e to the x to the third over 3 plus the constant. And then to solve for y, since we have the absolute value of y, we write y equals positive or negative e to the x to the third over 3 plus c. And then the initial condition is going to determine whether we use the positive or the negative. Okay, so the initial condition says when x is 0, y is 2. So when x is 0, y is equal to 2. So we can tell by looking that we're going to have the positive solution. But anyway, we need to determine what the value of c is. So replace y with 2. Replace x with 0. So 0 to the third divided by 3 is 0. So we just get 2 equals e to the c. Yeah, another way to write e to the x to the third over 3 plus c, I'll write it with the positive coefficient. But it's useful to remember that e to the x to the third over 3 plus c is the same as e to the c times e to the x to the third over 3. When the bases are the same and you're multiplying, you add the exponents. Hey, but we now know that e to the c is 2, so our function that we want is y equals 2 times e to the x to the third over 3. Okay, let's look at a couple more examples. Solve the initial value problem. Dy dx equals 3x squared plus 4x plus 2 over 2 times the quantity y minus 1. And the initial condition is y of 0 equals negative 1. Okay, we can separate this. So what should I put on the left-hand side? Assuming I leave dy on the left-hand side. Well, if we start with this equation, depends on what you want to do first, but if we multiply both sides by 2 times the quantity y minus 1, and then if we multiply both sides by dx, we'll get 2 times the quantity y minus 1 dy, and on the right-hand side, we'll get the quantity 3x squared plus 4x plus 2 dx. Okay, then put those inside integrals. So I'm going to go ahead and multiply 2 times the quantity y minus 1 and write it as 2y minus 2 dy. And then that's equal to the integral of 3x squared plus 4x plus 2 dx. And then integrate both sides. So on the left-hand side, we'll get y to the second minus 2y. On the right-hand side, we'll get x to the third plus 2x to the second plus 2x, and then plus a constant. Okay, we want to solve for y, so now what do? On the left-hand side, we have y to the second minus 2y. Before solving for y, let's use the initial condition to determine what the value of c is. So y of 0 equals -1. That just means that when x is 0, the value of y is -1. So we'll replace y with each of the y's with -1, replace each of the x's with 0, and then solve for c. Okay, so replace y with 0, we get -1 squared minus 2 times -1 equals c. So -1 squared is +1, and then minus -2 is +2. So the value of c is 3. Okay, so now I'll rewrite that equation with c in it. Y squared minus 2y equals x to the third plus 2x squared plus 2x plus 3. We want to solve for y, but we have y squared minus 2y. So any ideas? So what we're going to do is we're going to create a perfect square trinomial from y squared minus 2y. So we need to find a number to add to y squared minus 2y so that it's a perfect square trinomial. We want a perfect square trinomial because the two factors of a perfect square trinomial are identical. So in other words, after we complete the square, we'll be able to write it as a binomial squared. Okay, so if you have a quadratic expression like y squared minus 2y, when the coefficient of y squared is 1, the way that you the way that you create a perfect square trinomial is take half of the coefficient of y and square it, and then you add that number to both sides. So half of -2 is -1. When you square -1, you get +1. So we're going to add 1 to both sides of the equation. Three plus 1 is 4. The left-hand side is now a perfect square trinomial. That means we can write it as a binomial squared, y minus 1 squared equals the right-hand side. And then we apply the square root property. If y minus 1 squared equals this polynomial, then y minus 1 equals positive or negative square root of that polynomial. And how do we know whether we pick the positive or the negative solution? The goal is to solve for y, so let's just go ahead and add 1 to both sides. So positive and negative square root of x to the third plus 2x squared plus 2x plus 4. And then outside of the square root, we have plus 1. Well, the initial condition can help us again. So when x is 0, y is negative 1. So when x is 0, we have either the positive or the negative square root of 4 plus 1. The square root of 4 is 2. So it looks like we want the negative solution because negative 2 plus 1 is negative 1. That's what the initial condition says. So our solution for y is negative square root of x to the third plus 2x squared plus 2x plus 4, and then plus 1 on the outside. Okay, an integral equation. If you ever take an upper division applied mathematics course, you'll learn more about integral equations. So an integral equation is an equation that contains an unknown function y of x and an integral that involves y of x. So we want to solve this integral equation, and with this kind of integral equation, we can use it to find an initial condition. Okay, so y of x is equal to 2 plus this function of x. It's the definite integral from 2 to x, 2 up to x. The integrand is t minus t times y of t dt. So does something jump out at you as a way to find an initial condition? When is well, there's a number of answers, but if you have a definite integral, when is it always equal to 0? No matter what the integral is, or no matter what the function is, what are the limits of the integral if you always get 0? If the lower limit and the upper limit are the same number, right? Then the integral is 0. So the lower limit is 2. If we just pick x to be 2, so y of 2 is equal to 2 plus 0, because if the lower and upper limits of a definite integral are the same, the integral is 0. So our initial condition is y of 2 equals 2. Okay, that will help later on because we want to find what y of x is more explicitly. So now we compute the derivative. If y of x is 2 plus the definite integral from 2 to x of a function of t, then y prime of x is just what we get when we replace x with t. sorry, backwards, replace t with x. So I get y prime of x equals x minus x times y of x. We're just applying one of the fundamental theorems of calculus. So let's write y prime of x as dy dx. And I'll factor x out of both terms on the right-hand side, so we get x times the quantity 1 minus y. I'll just write it, instead of y of x, just 1 minus y. And we have a separable differential equation. It's a first-order equation, first-order differential equation that is separable. So when we separate it, we'll get dy over 1 minus y on the left-hand side, and on the right-hand side, we'll get x dx. Okay, then we integrate the left-hand side. So the integral of 1 over 1 minus y dy, and then the integral of the right-hand side, x dx. And the antiderivative of 1 over 1 minus y with respect to y is negative times the natural log of the absolute value of 1 minus y. And on the right-hand side, we get x to the second over 2 plus a constant. And then let's go ahead and multiply both sides by -1, so we get the natural log of the absolute value of 1 minus y equals the negative of x squared over 2 minus c. And then the absolute value of 1 minus y equals e to the, I'm going to write it in the simpler form, e to the negative c times e to the negative x squared over 2. So removing the absolute values, we get 1 minus y equals positive or negative e to the negative c times e to the negative x squared over 2. Okay, so we can solve for y. If we add y to both sides and subtract the positive or negative expression, we can write it as y equals 1 plus or minus e to the negative c times e to the negative x squared over 2. Okay, now we have to decide if the solution involves addition or subtraction. So that is where our initial condition comes in. So our initial condition tells us that y of 2 equals 2. Okay, so that indicates that well, this term right here, e to the negative c times e to the negative x squared divided by 2, that's always positive. So that means we have to have 1 plus. Okay, and let's see, when x is 2, we're going to get e to the negative 2. So it comes down to 1 plus e to the negative c times e to the negative 2. So when is, if you subtract 1 from both sides, when is e to the negative c times e to the negative 2 equal to 1? Yeah, when those exponents are negatives of each other, right? So in other words, if you have e to the negative c times e to the negative 2, that's e to the negative c minus 2, but that's equal to e to the 0. So we're trying to find the value of c. So negative c minus 2 equals 0. Add c to both sides, we get c equals negative 2. Okay, so our function then is, I need to raise it a little. Our function y is 1 plus, so if c is negative 2, this is just e to the second times e to the negative x squared over 2. That is our function. Hey, let's look at this word problem. Hey, this one says a container with 400 gallons of wine contains 20 gallons of alcohol. And then wine with 8% alcohol is pumped into the container at a rate of 5 gallons per minute. And then the mixture is pumped out at the same rate of 5 gallons per minute. Find the number of gallons of alcohol in the container after 1 hour. And then also find the percentages of alcohol in the container both before and after the hour-long pumping in and pumping out. Yes, so we're focusing on the number of gallons of alcohol that are in the 400 gallons. And we're starting out with 20 gallons of alcohol in the 400 gallons of wine. And then wine that is 8% alcohol is pumped into the container at 5 gallons per minute. And then we're assuming that it's thoroughly mixed and then pumped out at the same rate of 5 gallons per minute. Okay, so let's define capital A of T to be the number of gallons of alcohol. Number of gallons of alcohol. In the container at time t. So we have an initial condition. We're told that to start with, there are 20 gallons of alcohol in there, in the 400-gallon container. So that's our initial condition. And we're given information about the rate of change of the alcohol in the container with respect to time measured in minutes. So in other words, we're going to write down an equation that involves the derivative of the alcohol function with respect to time. Okay, so the derivative of A with respect to T, the units are gallons per minute. So this is the rate of change of the alcohol content measured in gallons of alcohol per minute. So we're told that wine that is a certain percent alcohol is pumped in, and simultaneously there's wine being pumped out that has a certain percent of alcohol. So what we have is, for this rate of change, we have a rate in and then minus a rate out. So let's focus on the rate in, see if we can come up with an expression for the rate of alcohol measured in gallons that's being pumped into the container. That's the rate in. Okay, so the rate of the wine being pumped in is 5 gallons per minute, and that wine is 8% alcohol. So if we multiply 0.08 times 5 gallons per minute, 5 gallons per minute, 0.08 times 5 tells us the rate at which the alcohol is being pumped into the container, right? Because 8% of the 5 gallons is alcohol. So 0.08 times 5 gallons of alcohol per minute. That's the unit for the rate in. Does that make sense? But then the thoroughly mixed wine is being pumped out at 5 gallons per minute. So what percent of the 5 gallons being pumped out is pure alcohol? Well, the total number of gallons of wine in the container is 400 gallons. The amount of alcohol in those 4 gallons is, the percent in decimal form is the number of gallons of alcohol divided by the total number of gallons in the container. Like, for example, if the amount of alcohol at time t is 40 gallons, then 40 out of 400 is 10%. So this represents the decimal form of the percent of alcohol in the container at time t. And we multiply that by 5 gallons per minute because it's being pumped out at 5 gallons per minute. Is this making sense? So at time t, that's what A represents. A of t divided by 400. It's the amount of alcohol in the container at time t. If you divide that by the total number of gallons of wine in the container, it gives us the decimal form of the percent of the alcohol at that instant. And it's being pumped out at 5 gallons per minute. So this is our differential equation that we can solve. So let's simplify it a little bit, simplify the numbers. So the derivative of a with respect to t, 0.08 times 5 is 0.4, and then minus 5a over 400, you can write that as a over 80. For convenience, we can think of 0.4 as 4 over 10, or 32 over 80. 32 over 80 minus a over 80 is 32 minus a over 80. Okay, and what we have is a separable differential equation. So on the left-hand side, we'll have the differential dA divided by 32 minus a. And on the right-hand side, we'll have 1/80th times dt. And then we proceed the way that we did with the other problems. The integral of dA over 32 minus a equals the integral of 1 over 80 dt. Okay, we're almost out of time. We'll just write down a couple more steps. On the left-hand side, we get the negative of the natural log of the absolute value of 32 minus a. On the right-hand side, 1 over 80 t plus a constant. Okay, I'll just keep going until we run out of time. Multiply both sides by -1, we get the natural log of 32 minus a equals negative 1/80th t minus c. And we're out of time. But we did have other problems that got to this point that is similar, so just go ahead and finish that one. Yeah, that's all for today.
Oh, and sorry about my email that I sent to the wrong professor.
Oh, about physics?
Yeah, that was
Yeah.
funny, but I'm sorry.
Did you also email your physics instructor?
Thanks, sorry.
That's all right.